Flow separation is an interesting aerodynamic concept. Essentially talks about, let's assume if a fluid is trying to flow over a certain surface, the inherent property of a fluid is that it always wants to stick to that particular surface. Now, due to several reasons, which range all the way from adverse pressure gradient to separation of your boundary layer and further things, the flow is going to no longer be attached to the surface of your body and it is going to move away from it. This is precisely what we are talking about when we say detachment of the flow or flow separation. The effects of flow separation are quite interesting in that they tend to induce a lot of aerodynamic drag. They also try to increase the skin friction drag, increase the pressure drag, so on and so forth. We always want to control this flow separation as much as possible, and if we want to implement these methods, there are various ways to do so as well.
Let's talk flow separation. So, flow separation essentially talks about the concept of having your fluid, which is acting on top of a surface, going away from that surface or breaking away. Initially, when we talk about having a fluid flow over a certain body or inside a certain body, the fluid tends to stick to the wall of that surface or the upper contour of that surface. Due to certain physical phenomena, the fluid tends to break away from that surface. It no longer follows that contour. This tends to manifest itself in the form of eddies, in the form of vortices. It has a profound effect on increasing your level of drag as well as reducing the amount of lift that is available to your particular body. Now, before understanding what precisely flow separation is, it's necessary for us to understand the two different physical phenomena here, Bernoulli's principle as well as the boundary layer separation. Both of these play a part in how your flow separation actually occurs in a particular scenario. Talking about Bernoulli's principle first, let's assume that we have a very simple pipe in front of us and there is a very simple inlet, there's a very simple outlet, and fluid essentially behaves in this particular way. We can see that the fluid is following a certain, parabolic sort of a profile, because the fluid near to the walls of the pipe tends to stick to those walls and fluid away from those walls tends to have higher velocity. Now, what exactly would happen if I would just pinch the middle a little bit and want to understand what is happening to my flow velocity in that instance? Well, the fluid tends to accelerate in regions where the area has reduced quite quickly, and it tends to reduce its velocity where the area has increased in that sense. Why does that happen?
So the Bernoulli's principle states that as area reduces, your fluid tends to accelerate. Why does that happen? Well, the fluid has to follow the conservation of mass principle, essentially meaning that as your area reduces, your fluid has to pass through it, meaning that the same amount of mass that has entered has to pass through a lower area. Now, this is precisely why you tend to see that as you hold the outlet of a pipe, the water that comes out of it is of faster velocity.
Now let's take an example here, an application of sort. Let's take this car that we have in front of us. If I were to zoom in very near to the body of this car and understand how the fluid velocity particles are actually behaving, we can see near, let's say, the hood of your car and the windshield, we have higher velocity, lower pressure. And as I move away towards the roof of my car, the velocity tends to reduce and there is a higher pressure in that sense. At the same time, as I keep moving further away, the flow has sort of detached from my surface, and essentially what has happened is the fluid has broken away from my car. Now, one of the most important things for us to consider here is that the fluid is at rest and the car is something that is in motion. Since car is moving, it is accelerating the static fluid particles or air in this instance and carrying it along with the surface of the car. And since the wall of my car is having the fluid particles stick on top of it, it is carrying these particles with it till a certain distance. Now, due to differences in pressure, due to inherent, changes in how the fluids are behaving when they are in motion along with the car versus when the bulk of the fluid is static, the fluid tends to separate as we move away from this particular car, and we'll try to understand why exactly does that happen.
So finally, how does flow separation occur? Well, as the moving body is moving against stationary fluid, this stationary fluid is going to act as a sort of barrier or wall. It is not going to let the moving fluid along with the body pass through it. This is what essentially causes what we call as the tunneling effect across the top end of your car. And this is precisely why, as the area is reduced, the fluid tends to accelerate in these regions. Now, this phenomena is prevalent everywhere in the physical world, all the way from cars to ships, boats, and even aircrafts. For the intents of this particular video, let's stick to automotive itself. Let's take a look at why exactly does your flow separate? What are the individual physical phenomena that come into play?
So this is your static fluid, uh, essentially air, assuming that there is no crosswind or there is no disturbance in the static air. Uh, the fluid particles that are coming with the particular car body are represented here in this red color, and as the fluid particles move along, it has a profound effect on how the static fluid particles are also going to move along with it, right? And this is what is essentially causing an energy transfer between the two molecules here, one that is stuck to the car versus one that is not stuck to the car. So the car body, which is carrying these fluid particles, essentially is ignoring a certain region. It is not letting the fluid pass by these certain regions. If we take a bulk of the fluid in that sense, let's try to understand why that is with another phenomena as well. Let's take another example here. Let's have the wind turbine that is spinning right there and understand how the fluid flow is going to essentially behave around a particular blade. Now, if I was to take this particular wind turbine and have a cross section of one of the blades here, then the blade would look more or less like this as an assumption. And as the blades are moving, the blade that we have airfoil right here is also going to move in a particular direction. Now, it's necessary for us to understand that the oncoming air is sort of flowing through this wind turbine blades, and that is causing the turbines to move inherently. Now, as they are moving, the flow profile that gets created looks somewhat more or less like this. Now, there are regions here where we can see that fluid is not exactly following the entire contour of my particular airfoil shape here. Again, it is separating away from my blade due to how it is oriented, and at the same time due to pressure differences as well. Now let's understand a very important concept here. This is boundary layer. Let's take a simple example of flow over a certain cylinder, a very circular level object here. The flow would more or less tend to behave somewhat like this here. And if I were to zoom in to the body of the cylinder here, the body would again have the flow look somewhat like this. And towards the back end of my particular cylinder, I would see these eddies that are formed. These are your recirculations that get formed due to your flow separation itself. Let's try to understand why that happens as well. So as I zoom in closer to my particular cylinder, I can see that the velocity profile that gets generated at different locations on my particular cylinder are of different shapes. Now, it's necessary for us to get into the concept of boundary layer or the sublayers as well, where closest to the body, the fluid tends to stick to that surface and the velocity is always going to be zero for our considerations. We call that no slip condition. And as we quickly move away from the surface in a normal direction, surface normal, the velocity is going to very sharply increase. And this in and of itself has a correlation with your Reynolds number, in that the flow transitions from laminar to turbulent as quickly as it can based on the inlet velocities. Now, at these different locations, we can see that the fluid is manifesting the boundary layer in the different shapes that we can see here. Now, closest to the cylinder, the boundary layer looks, quite simple here. The velocity is 0, and as we keep moving away, the velocity keeps increasing. Now, the next point here, this is closest to the 90-degree point here of the cylinder. The velocity is quite reduced. Even the topmost layer that we have here, the velocity has quite reduced in that sense. This tells me that fluid is trying to move away from my particular cylinder. And the third part, the sharp change is quite apparent here, where we can see that closer to the wall of my cylinder, the air essentially, or the fluid, is not at all present in these regions. Hence, the velocity is as less as it gets. And the final point here, we can see a certain flow reversal as well. Why exactly is this happening? Let's have a deep dive into why is there a flow reversal that has occurred and then in turn given us these eddies as well. So from what we can see here, there is a high pressure region versus a low pressure region. One of the fundamental concepts of fluids is that your fluid is always trying to move from high pressure to low pressure. And whenever that occurs, it effectively means that there are more molecules that are present in one point and there are lesser molecules present on the other side. And the higher level of molecules want to move to lower level molecules. That's the whole idea. Now, as we grow closer to the particular cylinder here, it becomes apparent that there is a higher pressure region that is getting created near to the wall. This is happening exactly because as your fluid is moving away from the cylinder, the presence of static fluid is higher near to the wall, whereas presence of moving fluid is lesser near to the wall at this particular location. Now, since that is occurring and we have a higher pressure region versus a lower pressure region, the flow tends to reverse its particular direction and we tend to see these eddies manifest themselves. This is precisely why majorly the Bernoulli's principle coming into play as well as the boundary layer separation coming into play both constitute why exactly is it that your flow separation is actually happening. Now, let's take a interesting approach towards understanding what this physical phenomena looks like numerically using OpenFOAM. So I'll talk about the tutorial problem that we have with vortex shedding. I'll discuss essentially the physics of it and explain about what do the results exactly mean and what can we infer from it.
Now that we have a grip on the theory, let's jump into the analytics for a little bit. Let's delve a little deeper into the mathematics part of it. One of the greatest tools that are available for analyzing flows and predicting flow behavior is computational fluid dynamics. We can use CFD to essentially understand how fluids are behaving and after a certain period of time or its interaction with a certain surface, how it may behave. One of the greatest examples that we can take in this instance is flow over a cylinder. This is what is referred to as a benchmark problem. Let's take a look at that.
Hold on. So why cylinder? Cylinder as a shape is quite interesting in that it is circular in nature, it is symmetrical in nature, but along with that, flow over cylinder gives us profound insights into how exactly is your fluid going to behave around such a basic shape. At the same time, a lot of engineering applications tend to have circular cross sections, whether it is a wind turbine or whether it is a antenna across a submarine and so on and so forth. The effects of having flow past a particular circular cylinder tends to really give you insights about how that machinery or part is going to behave, understand its effectiveness as well, because flow over cylinder, as we see, is also giving rise to this vortex induced vibrations or movement of your particular part itself. So when you see trees that are swinging in one point, or if you see farms, you see a lot of the different applications that we have in the real world, even the aircrafts, the vortices that gets induced due to your flow separation have a profound effect on how the movement of your object is going to be. And this is precisely why we want to understand how fluid flow is behaving across a particular cylinder.